All right. So I think Khan covered everything, so I can skip my talk because he covered everything related to irrigation. But anyway, I'm focusing this presentation on method and tool for irrigation scheduling, and what I plan to cover in the next, let's say, half an hour is review some basics of crop water use, but very little, and then talk about method and tools for scheduling irrigation, and somehow discuss advantages and drawbacks of these methods. And I'll give you at the end my take on how I think this piece of work should be done in terms of tools and method to be used in the field. So what really, so this morning we had several presentations on the crop evapotranspiration, or it really drives the crop evapotranspiration. It's been said several times that really the solar radiation is the main source for crop water use. And so in reality, it is the main source, but has different forms. So it could be the energy directly intercepted by the canopy, or what the canopy will encounter as an indirect source of energy. It could be warm air moving from one place to the other, and in this also wind makes a difference. So a windy place for sure has a higher ET than a non-windy place, and also the row orientation makes a difference because it depends on the wind direction and the row orientation, because this can cause a little bit more turbulence and take more water out of the crop. It's also cases of advection of warm air masses that move from, especially when your vineyard it's isolated in the middle of fallow land, and so the heat that comes from around your vineyard and then moves towards your vineyards, that also a source of energy. So what really the combined effect of this direct and indirect energy sources on the plant canopy determine the water use. This when the soil moisture is not limited, and because if soil is available in the soil, if the water is available in the soil, that flow of water can go through the crop, and the plant can transpire. When you start having limitation, that energy generates heat, and that heat doesn't generate necessarily evapotranspiration, but might generate higher temperature around the canopy. All right, and so the soil moisture is an important factor when you have the energy hitting on the canopy. You have to have water in the soil to move that pump, because the plant is really a pump that pump water out of the soil and transpire water through the leaves and the rest of the canopy. So this morning also there was a presentation showing that there are different methods for estimating and measuring. So we are using some of this method in vineyards, and you can see some picture of one of our research experiments in the Sierra foothills in El Dorado County with Lynn Wunderlich as a farm advisor in the Central Sierra. And so you can see there a picture of the surface renewal and anticovariance tower here in the in these two pictures, and you can see sonic anemometer, different sensor that at the end will give you the evapotranspiration as a residual of the energy balance. Okay, but at the same time, when we do this, we also measure the soil moisture, and at the same time, we measure somehow the plant water status in order to make sure we're measuring something that is unlimited. Okay, so what I think this morning has been missed is that what really drives evapotranspiration during the energy limited stage is the solar radiation. And the energy limited stage, it means that everything else is unlimited. So the soil moisture can feed the plant for that evapotranspiration. When you start having limitation in the soil moisture, then there are other factors, physiological factors that intervene and somehow regulate the actual water use with respect to that potential water use we were talking about this morning. So when we come to scheduling irrigation, this is really a topic that allows you to understand, to answer several questions. First of all, when to irrigate a crop. And the old old-fashioned engineering school was saying that irrigation was for full replenishment of ET, okay, for field crops, for example. So the criteria was to irrigate before the plant face any water deficit or any water stress. But now in the last 20 to 25 years, so the research show that some stress might be beneficial for quality of production, like an example in almonds or grapes or wine grapes, it could be beneficial. And so the new answer to that question is either before plant face the water stress or at a specific level of that deficit that will allow you to achieve some quality of production, right? So how much water to apply is the second question. And again, the old-fashioned irrigation engineering school was saying, you know, that the amount of water that the plant has transpired since the previous irrigation or rainfall. That, again, is a full replenishment. But again, now we are talking about wine grapes, so it could be a portion of that. It doesn't have to be necessarily the full amount of water that the plant has transpired, or portion of the maximum potential ET of your grapes. And the third question is how to best apply that water. Do we have to apply that water uniformly or site-specifically? All school would say yes, because they were not easy to spot the difference in the spatial differences in the soil and plants. So in that case, distribution uniformity was really a criteria. And, or, you know, now we got a crop planted in marginal soil where spatial variability is an issue. And so Ken will give a presentation later talking about the site-specific and spatially variable situation. And we got a lot of this now. Or the other question is, do we have to apply long and deep irrigation or very frequent and light irrigation? Because there's another question that refers to irrigation scheduling. And there's different thoughts and different situations. And the third one is the application rate, so the amount of water we apply has to be compatible with the soil infiltration, as I explained this morning, and the water holding capacity. Or if the soil allows, maybe it should be higher and, you know, benefit from energy rates and energy consideration. Anyway, so we got basically three methods. I would say now there are four, but the basic three methods for irrigation scheduling are weather-based, soil-based, and plant-based. And the weather-based is basically what we talked about this morning, is somehow calculating, estimating the evapotranspiration of the crop. Okay, so the crop water use that we call ET, crop evapotranspiration. It's very common. It was very common in the past, but requires some calculation and some adjustment also. The soil-based, what we do, we try to deploy some tools to assess the soil water status, and we assume that the plant follows the soil water status pretty well. And this is equipment intensive, especially now because we have spatially variable soil. So the question is where to place this in a representative area. That's too easy because I got, you know, so many different situations now, especially because crops are planted in marginal soils. But also, it's a good way to check if your schedule, once you come up with a schedule, if your schedule is somehow effective, you are achieving what you're planning to achieve, what you have in mind to achieve. The third one is a plant-based. So what we try to monitor is the plant water status, because the plant integrates what it feels in the soil and what it feels around the canopy. So somehow is more representative of the plant itself. It's centered on the plant, although there might be some spatial variability in the plant water status, right? And so the question is, what plant do we monitor in that case? But anyway, it's a labor intensive because, you know, normally is done through non-automated procedure like stem water potential, leaf water potential. You got to have people in the field at specific time during the day to do all this measurement. So it's labor intensive. It's also well developed for some of the crop, but not for all. In case of wine grapes, I think is well developed now. The threshold for stress, non-stress, or mild stress are somehow well known thanks to the work that Dr. Williams and other people have done in the past. But, you know, for other crops is not so well developed. And they need somehow some site-specific calibration. So in any case, all irrigation scheduling methods somehow require skilled people. So you have to have skilled people on the farm. And these skilled people have to be somehow reacting and troubleshooting for stuff that doesn't work. Most of the time the technology is very good in the lab. When you deploy in the field, sometimes, it gives data that you don't understand. So there's some adjustment to be done or some troubleshooting. It happens all the time because this is stuff that is under the different type of weather. So the first method, it's ET-based scheduling. As I was mentioning, the basic criteria is replenish the amount of water that is used by the crops since the last irrigation or rainfall event. Normally in California, we estimate crop ET as a product of reference ET, which is the amount of water used by a reference grass surface without any water limitation and any nutrient limitation. So we refer everything to grass, okay, and we somehow estimate how much water is taken by our crop through this, what they call fudge factor or adjustment factor, which is a crop coefficient. So we got three possibilities here. Either we can use historical average ET that are available somehow for the different parts of the state. It could be historical crop ET or historical reference ET. But anyway, we need some kind of accurate crop coefficient value there. Or we can use real-time reference ET that's available at free of charge. But at the same time, we need good value of the crop coefficient. Or we can use somehow forecast ET for the week to come or the 2 weeks to come. In any case, we need some kind of accurate. So the critical part is always not really the reference ET or historical crop ET. The critical part is the crop coefficient value. This is an example of information you can find from ITRC at Cal Poly. They put together for different zones, for different areas in California, the historical average crop coefficient for, crop ET for different crops. I was looking in this webpage and, there's many crops. You got a sense of, how much water is required by different crops. Grapes is not there. For some reason, probably they didn't want to mess up with the complication of grapes. So looking there, and wine grapes is not there. So probably they want to save all the burden to provide kind of a misleading information. But anyway, this is a source of information if you have other crops than grapes. We also have the historical reference ET are available from CIMIS, and CIMIS has somehow divided the California into, I think there are 16 zones. And for instance, if you consider one of the 18 zones, zone 10, you get a sense of how much water is used by grass per different month over the year. And at the same time, you need a crop coefficient. So I was looking in several publications. I found somehow an old crop coefficient set of value developed for the Central Valley of California from research done about 15 to 20 years ago. And as you can see, I marked this crop coefficient for the area of Lodi, and they were related to grapes at 50% canopy cover as a maximum canopy cover. Again, you got a lot of information on reference ET. You got also a possibility to forecast that, and this is what is called FRECT, forecast ET, and is available for the whole United States. And I use this sometime when I have to schedule irrigation for my project in citrus. I do it. You can see here again. You can see here, the forecast ET for the following 7 days of the week, and this is very useful for growers as long as they have a sense of the crop coefficient. Anyway, it's another source of information. So the critical part is really for scheduling irrigation with ET-based scheduling is really having a good crop coefficient value. The drawbacks of this is if you take the crop coefficient developed from an area and you apply it to your site-specific condition, it might be good, or you might be running the risk of over-irrigation or under-irrigation, because in your vineyard, situation might be, the soil situation might be different, the canopy situation might be different with respect to the vineyard where this crop coefficient were developed. In fact, most of the available KC information for different crops, I'm not talking only about grapes, was developed for infrequent irrigation, so either sprinkler or surface irrigation method, was developed for well-drained soil, that makes a lot of difference, and for flat, ground level, okay? And also was developed for crop varieties and rootstock and planting density, canopy management. We're very different with respect to what we have now. I'm talking in general, all right? And so the other thing is the micro-irrigation is really a game changer because you spoon feed the crop with water and nutrient, and that keeps the root system somehow confined in the first 2 or 3 feet of soil, and somehow the plant gets spoiled by this type of irrigation management, so somehow doesn't react, doesn't have a deeper root system. So, and also, you know, micro-irrigation generates a faster canopy growth and also a larger canopy growth in time. So my take is that only looking at ET might be somehow misleading when you have very valuable fruit and nut crops in California. And probably the best way is to look at the plant and how the plant feels it and somehow the soil water status together with the plant. So ideally, you know, you get the chance to measure stuff in your site-specific condition, like this morning Chatapau has talked about the Thule that gives you a site-specific estimate that is somehow measure a blend of measurement and estimation, but it somehow is representative of the site-specific condition of your canopy, your soil, your irrigation practices. We got possibility to measure with research scale, but this is not operational. I want to show you some results that I put together in the last few days for a research project that we had in the Sierra foothills for about 3 years, actually 4 years. So we got a vineyard, Cabernet Sauvignon, Clone 15, planted in 2000 with certain density of 3,703 vines per hectare. The spacing was about 1.8 by 1.5 meter. The vine rows were oriented in north-south direction, and this was planted on a sloping field. So one had south-facing sloping, and the other one had north-facing sloping. And so the soil, and there was some difference in the soil, but anyway, they were adjacent, so the same area. And the slope that we measured in the north sloping area was about 24%, and the other, in the south were 25%. So very similar. Here's what we found. This you can see here in this graph the measure ET of the two sloping area. More or less, they are the same at the end of the season, but during the season, there's some different distribution, right? And this is basically what we think is the amount of solar radiation that is intercepted by the crop is different because you have a south-facing and a north-facing. Originally, this was our thought. But what I think is important here is when you measure, you get a sense of what is going on. Growers were irrigating at about 8 to 9 inches over that season. This is 2016, and we measured about 17. So growers were thinking he was doing deficit irrigation. The plant was transpiring without problem. So if you don't measure, this is a significant difference with respect to what the grower estimated was at DT, and so they apply water. And in that area, they're interested in producing yield, so mass. They're not super interested in producing quality. Okay? And you can see here there's a significant difference from the real ET that we measure and the applied water. All right? So that gives you a sense of, you know, how measurement clarify things instead of estimating things. And this graph was surprising for the grower because he said, no, I don't think he's taking so much water. Well, this is what we measured. somehow. And these are related to the discussion that we had this morning. This is for the 3 years, the measurement of net radiation. So we said net radiation this morning is really the driving force of ET. And you can see those are the weekly accumulated net radiation for north and south. And you can see the north is in blue and the south is in red. And you can see a clear trend there. At the beginning of the season, the north was transpiring, somehow was receiving more radiation, probably because of the solar angle. Around the solstice, so June, those two net radiation were pretty similar. And again, they parted away later in the season. So early in the season and later in the season, the net radiation that the plant was receiving, which is the energy available to do the work for evapotranspiration, was different. And so we cannot apply there something that was developed for flat area because of the slope and aspect. Right? And this is the case of many wine grape growing area in California. They're now developed in hillside terrain. You can see 2017, we got a different situation, 2018, another different situation. So, and here is the weekly average crop coefficient that we derived in the north and the south. See how, this is a weekly average, so it's supposed to smooth all the fluctuation. But see, we see also a clear trend there, but things are not following exactly net radiation because this is not a level area. So how do you manage irrigation here? So when we have to provide information, we say, well, probably best thing to do is measuring and applying water according to a certain strategy. Okay? And this is the midday stand water potential that we measure over the season. Okay? So we assume everything is the same, like the canopy cover is the same, the soil is the same, the plant is receiving this amount of energy at the same level. But in reality, things were different in the two sloping area. And also the growers was thinking that he was applying the same amount of water at the 2 blocks because it was the same management. And in reality, it was not. So when it comes to sloping situation, it's really complicated to draw a conclusion. Now, there's a lot of information now that is available that is somehow helping because the work that Dr. Williams did in the past showed that there's a clear linear relationship between the shaded, the percentage of ground surface shaded area by the vines and the crop coefficient. So we said, okay, let's try and let's see whether it works. Okay, this is a calculation example of how you somehow derive the crop coefficient for a 7-foot vine spacing with a certain shaded area. Okay, so we said, okay, let's try. So we measure the light interception with the Paso panel, which is a tool that is going to be explained tomorrow in the field. And so we saw that the north block was developing faster and was having a bigger canopy than the south block. And this is somehow not surprising because the south were probably receiving too much heat. And so that heat was restricting the growth or making the growth proceed with less rate. I mean, and this is a graph of the light interception that we measured in north and south. So as you can see, the light interception in the north was higher and then in the south. Now we said, okay, let's see. This is the blue is the ET that we measured. The green is the ET that we calculated following the canopy shaded area and the Dr. Williams model to calculate. And this is the ETC that we estimated from the Central Valley crop coefficient. And you can see, I cannot draw a conclusion here. I can say, oh, I'm very confused because, none of the model or none of the estimation for flat area can work in sloping area, to my understanding, and need adjustment. Need adjustment coefficient to when we move from a flat area to a slope area. And it depends on the slope, and it depends on the aspect. So here you can see our ET was somehow different from all the other ET curve. The ET that we measured was different. So how we manage this irrigation in this complicated situation, which is simple somehow because it's representative of a lot of growing area in California now when you have sloping terrains. And so I really don't know what to say, rather than why don't we measure it? Now there's tools to measure it and to follow up and provide and somehow schedule irrigation based on some smart, intelligent system. Okay, so moving from ET to soil moisture. This is a second type of method that a lot of people apply. The soil moisture-based irrigation scheduling is based on observation on how your soil water changes over time. And we start irrigation at a certain threshold level. When we reach a certain threshold, then we apply some irrigation there. And we stop irrigation when the soil moisture is brought back to a certain level that we consider optimum. So it really keeps track of what happens in the root zone with regard to how much water infiltrates during an irrigation, how much water is depleted in between irrigation, and how we can maintain that soil moisture at optimal level for our yield or quality target. This is the principle of operation of soil moisture-based irrigation. So we basically can answer a few questions of when to start irrigation and when to stop it. Also, we can see whether it has enough water infiltrated in the soil or it was insufficient or was too much, and whether we are applying this the way we think we are applying. And also, the other question is there any deep water reserve that could be tapped by the crop in periods where you have to stop irrigation, either harvest or a bud break, or, I don't know, when your pump is not working for some reason, your irrigation system is failing. Is there any deep soil water reserve that we created or the rainfall has created that the plant can tap when we have problem in the field? So we can measure soil moisture in terms of soil moisture content or soil moisture tension. And those are two different type of units. The soil moisture content, it could be inches per feet of soil, or millimeter per meter, or percentage. The soil moisture tension is usually measured in centibar or a kilopascal. I personally prefer the soil moisture tension because it gives you an idea. So the drier the soil, the higher is the tension. So the more negative is the tension. So it means the plant has to exert a lot more energy to pull out that water from the dry soil. Okay. So there's a plethora of sensors in the market that can give you an idea of soil moisture content or soil moisture tension. In any case, they measure some specific characteristic of the soil, and then it converts into tension or volumetric water content through some calibration factor. We got the simplest one are the gypsum block as a soil water tension tool, or sometimes we use the watermarks, and those have different advantages and disadvantages. The gypsum block is very cheap and maintenance-free, can last for several years, but they are sensitive to soil temperature, so sometimes gives spikes when the soil heats up because it's dry, or you got some ground heat flux, and also they're subject to corrosion of the electrodes. The watermarks have several advantages. Also, they're maintenance-free, they don't require further calculation, easy to interpret, and somehow they account for the salinity. We might change the reading up to a certain level. 4 or 5 decisiemens per meter, they're fine. Beyond that level, we don't know. This is an example of installation, what we did in Safari in our research. We got a 12, a 24, a 36. We wanted to put it down to see whether there was some soil water reserve, but we hit the bedrock here. We hit the rocks, and we cannot. In one case, we could not even reach 24. We had to move on the other side because sometimes you hit stones and you have to move to another place. Here is some values based on the type of soil. soil texture, and it gives you some guidelines when the plants will start feeling some stress. This is for soil moisture content. That is for soil moisture tension. You can see sand, sandy loam, loam, and clay loam have different value because the water is retained with different forces in different type of soil depending on the content of clay particle. What I think is the drawback of soil moisture scheduling is we got a lot of example of even when the water is, there's a good soil moisture there, the plant is showing stress. And we got a lot of example now in the Central Valley because now it's being planted on marginal soils. So sometimes we have situation where the soil is showing, oh, you're good. You don't have to do anything. The plant feels the stress. And that happens because of salinity, sodicity, so you cannot spot this problem easily with the soil moisture. But look here. There's a saline soil, and it shows that the soil moisture is pretty good. No problem. But the plants were feeling a lot of stress. So the stem water potential was showing the stress. The soil was not showing any problem. And sometimes we have compaction layer. So you irrigate and the water piles up, and you got hypoxia or asphyxia. So there is some limitation there. There's some more limitation because you got in some type of soil, you got some preferential flow of water. So it depends where you place your sensor. You place it here, you place it here. It might be some kind of misleading. And this is one of the reasons why I don't think the soil moisture balance method works in irrigation scheduling with micro-irrigation. This is one example. What volume of soil do you consider? I don't know. I mean, there's so many situations like this now because of marginal soils. So these are some other limitations of soil moisture. But anyway, we can use it as a feedback to see, are we irrigating correctly somehow? Do we get some feedback from after an irrigation, after 3-4 hours? Let's see where the soil moisture is. But we need really to look at the plant. Because the plant, again, it integrates everything that is happening. So we got different tools that are available to look at the plant water status, like leaf or stem water potential. We got sap flow. We got also some canopy temperature measurement. All of them somehow are based on some calibrated value that will give you some threshold where the plant is feeling the stress or not. So some of the methods are well developed for different crops, some other are not. So we're still at the research stage. I'm not going to concentrate on the pressure chamber, on leaves or stem water potential because I'm pretty sure everybody is familiar with this. We got some other plant sensor that we're using in some of the research projects that we're using, like the dendrometer. A dendrometer somehow feels the shrinking and the swelling of the trunk as a result of the energy that the plant exert to pull out water from the soil. So a stress, let's say, a non-well water tree or vine will probably have more shrinking and swelling than a well-watered plant. But again, it needs to be calibrated versus some other parameter. So here is an example of the infrared thermometer. And the other one shows an example of the leaf sensor, somehow that measures the turgor of the leaves. And that is somehow another new type of sensor that is coming into play. And so we don't know much about this, but it exists and might give you some indication. What I think we really should do for high-value crop is a combination of the different approaches. So use a plant-based system like something to monitor the plant water status over time in order to decide the timing. When is the time to irrigate? And somehow have a sense of ET, of the actual evapotranspiration. If we can measure it, it's probably ideal. And then in order to apply the adequate amount of water for reaching our target situation for the plant. And use the soil as a feedback. So after we decided the timing and the amount, then we check on the soil. Are we doing this thing correctly? And it depends whether we have a system that applies something that I talked about this morning, the system that applies what you think is applying. So somehow using the combination of this, you can get a sense of whether you're doing a good job or not. But also another check for feedback could be coming from the flow meter, because it can give you a sense of how much water you're applying to get to that situation. I'll probably stop here because I don't want to complicate more your ideas, but I would say for crops that are important in terms of where quality is important, observing and monitoring the plant probably is the best thing to do, rather than assuming that something that was measured somewhere else can work in your site-specific situation, because your soil, plant, canopy management, planting density, slope, and aspect, might be very different from, an average situation was measured somewhere else. I'll stop here and I'll take some questions if you have. Otherwise, I'll enjoy the rest of the presentations.
Here's a question. Can I see your slide on stem water release?
Yes. I think it was, the last one, the last graph on the bottom. Up to a certain point, I think we will get a little 6 bars per stretch. Yeah, at that point, yes. But here we got a strange situation. There was a leak in the north part, and so
that wasn't due to anything you're doing.
No, that was probably a leak in the system that I've got unnoticed for more than a month, and that inverted the situation. But you can see from probably, I would say, mid-June, yes.
And what was the second one of graphs going down from top? What's that data?
It's the weekly average actual crop coefficient.
And how was that determined?
From the actual evapotranspiration that we measured, divided by the reference ET. What we call it actual crop coefficient. We don't call crop coefficient because it gives a sense that normalized based on the weather, let's say the water demand of the atmosphere. Yeah. Well, we don't see, I'm not saying that this is the crop coefficient that should be followed. No, this is what we measured that we wanted to normalize in terms of the water demand. But, yeah. All right.
The portion of the vineyard was subjected to a fire, the wildfire right next to the vineyard as well.
Yeah, that was in August. I think it was in August. The fire came, and we saw the spikes in the sensible heat flux in our measurement station due to the fire. It didn't catch fire, but it was stopped.
It didn't catch fire.
No, it didn't catch fire. All right.